Let's get rolling. So, we are in the midst. Oh man, we once again not streaming the right. Hold on. Come on, we got to start here. What do you mean? No, we won't. Sorry, technical issues. Okay, we're gonna.
No one like that.
That's fine, but it'll be okay for now. Okay. So last time we started out talking about crypto. We launched the crypto module and we dug in to Diffie-Hellman, did some Diffie-Hellman work in IPython, and started in on RSA. This class, we're gonna keep pushing forward on RSA and then talk about AES chaining or cipher block mode of operations. All right, any questions before we get started about Diffie-Hellman or the parts of RSA that we covered? All right, who here has gotten to the RSA levels yet? Nobody. Who here has gotten to the AES levels yet? All right, who here has gotten through the AES levels? Not yet. Okay, hopefully by the end of the day, you'll have everything you need to push through, but I guess it depends also on how many crazy tangents we go off on two. All right. Let's roll. So we are started. We've got the desktop up. Everything is great. We will maximize this. That did nothing. Okay. We really can't maximize this one time. Oh, we can maximize this whole guy. Wait, what? You can't?
It's probably too zoomed in for the, I think, the bar thing disappears. Now it's there. So now you can click it, top right.
Oh, this guy disappears, sure. But what about this guy? There should be a full screen mode. All right, it doesn't matter. Okay. So we're back in IPython before the Twitch says there's an echo. Oh, God damn. One second. Test. Oh, yeah, there's an echo. All right. This should be better. Let's, wow, a lot of people complain about the echo. Okay, it's gone. Perfect. All right. So, as a quick ramp up through the last class to this class, we had M. M was our message that we wanted to encrypt with RSA. We had N was a module under which we were operating, and N was the product of two primes, P and Q. And P and Q were just a bunch of large primes. But we're going to back up a little bit and recall with Diffie-Hellman, we had just one prime that we were operating under the modulo of. And that prime was P, right? And if you recall, with Diffie-Hellman, we had P equals some prime, say 71. And me and Connor each came up with numbers. My number, I don't know, 15. Connor's number is 25. We exchanged with each other to our number, modulo P, to Connor's number, modulo P. And then we raised that. So Connor would receive this, not knowing what lowercase y was. And he would raise it to his number, modulo P. And I would do the same, receiving Connor's number, not knowing what the original number was, just knowing what his public number was, modulo P, and we'd arrive at the same shared secret. That's Diffie-Hellman in 10 seconds, right? Now, all of this works because it's very hard to do a thing called discrete logarithms to recover from 2 to the Connor number back to Connor number. Normally, I would be able to take the log 2 of 2 to the Connor number, right? So if I did just normally 2 to the Connor number without mod p, and then I did this, and I did math, that log 2, I could recover Connor's number. But I can't do that because we're operating on a modulo, and in conceptually speaking, we keep looping over at 71, right? So this 33 million or whatever this is, it's really just like a bunch of times around our 71 numbers, and it's hard to understand where we started. We don't have a good algorithm to do that as you know, computer scientists, and so we just can't really carry this out without a quantum computer. Cool. So it's, you know, we have algorithms that will run on a quantum computer. We just don't have publicly known quantum computers that are good enough to run these algorithms, so they actually make a difference at the size of data that we're typically operating under. All right. Awesome. That's Diffie-Hellman. And then we said, hey, what if we didn't just want to come up with some random number, like Connor and I came up with a shared random number. What if you wanted to come up with a, what if we wanted to pass messages back and forth? We wanted to control the contents of this. Well, Diffie-Hellman's no good, because all that we have control over, me as a as Jan, the information secret to me, is just this lowercase y, right? I don't know Connor's lowercase c, so I don't really know, or yeah, lowercase c. So it's hard for me to figure out privately. I guess now I'm trying to think of the crypto system as I'm saying this, but basically, this isn't a data exchange crypto system. It's a signal, like a key exchange, a key generation crypto system. Okay, if we wanted to exchange data, we need a scenario where the correct solution, by the way, to exchange data is what you do in the challenges, which is you use Diffie-Hellman to create a key, to exchange a key that is used by AES to secure the rest of the communication, right? But if you wanted to maintain this certain other properties where, let's say, without having to come up with a key exchange interactively, I wanted Connor to be able to send me encrypted information, I want to decrypt it, right? For this asymmetric cryptography, we need something else, and that something else is RSA. And we're going to dive through RSA. Yesterday, we kind of hit RSA. It was like 240 or something, and we had to speed through. We're going to take a little bit of time right now and go through it calmly. All right. So you recall the discrete log problem is pretty tricky. That's kind of one tricky problem that happens under a modulus. The other tricky problem is factoring, and we'll get to why that's relevant for RSA. But RSA is basically this. In the modulus, or in the an exponent, hold on, trying to, this would be much better after the at the tail end of the last class. We can just maybe put the two classes together when we upload this. When you're operating under a modulus, right? You can, we went through why, you know, you could take, I don't know, if our modulus, our field operating under a modulus of 71 or defined under modulus of 71, we can multiply, you know, two numbers and take a modulus of these. Boom, 21. We can multiply them and do whatever operations on them, and then take the modulus, and that works out great as well. But then we mentioned, oh, there's this one kind of special case, right? if you wanted to say, okay, we got 10 plus 27 times 35 mod p, and then we did 27 times 35, and we did that mod p. Cool. And so then we did 10 plus 22 mod p. I mean, it doesn't even need to be modded, but yes, the same 32 going step by step, and first modding out, calculating the result under the modulus of all the individual components, and then putting it together as it is, first calculating out the large number without the modulus, and then taking the modulus, right? But there's one place where that's not the case, and that's exponentiation. So if you do this, 27 times 35. So this is 10 to the 27 times 35 power mod p. We end up with 1. Let's do a different example. 11. Okay, we end up with 70. Very cool. If we do, again, 27 times 35 mod p is 22. So if we do 11 to the 22nd power mod p, we get something different. Why do we get something different? Because of a interesting, tricky part of basically finite field math, where exponentiation happens. Exponentiation in a finite field under modulo p happens under a different modulo, right? So if normally we're under mod p, in this case, the stuff that's in here that's in the exponent happens under what's called the totient of p. And the totient for a prime is just defined as p minus 1. All right? So then, if you want to compute this same thing here, we got 70. We take 27 times 35, and we mod it by p minus 1. That's 35 now, not 22, not 32, as if we were modding by p. And then we do 10 to the 35. There's our 70 back. All right? And the world makes sense again. So when we're working in a finite field, we can typically split up our different operations, modularize them early, modularize them late. It's not a huge deal unless we're working with an exponent. And in Diffie-Hellman, we don't work with exponents. We're just multiplying, and life is nice and easy. And we don't even have to think about Euler's totient function in our worst nightmares. But in RSA, we do, right? Because RSA works on this exponentiation, and we'll dig into why this exponentiation maybe basically makes RSA work. So outside of an exponent, mod p, we're in totient of p, which is p minus 1. Inside of an exponent, sorry, outside of the exponent, we're just mod p. Inside the exponent, we're mod totient of p. That's when p is prime. So let's design a crypto system. Let's look at RSA with a prime p. All right. RSA is based around this concept of exponentiating a message to encrypt it. So my public key is going to be a large, we'll start with a large P. So this is single prime RSA. This doesn't exist. We're using this for teaching purposes. So our P, again, is 71. And we're going to say, hey, we're going to encrypt. Going to take an encryption key. I don't know. Let's make it 3. Right? So now we have 71 and 3 are our public key. What I'm telling everyone is, hey, if you want to encrypt a message and send it to me, these are the numbers that you need to do it. When you send me a message, if you want to send me the number 5, let's do something bigger. I don't know. Let's do 11 again. You would raise it to the e power You'd mod it by P, and you'd shoot it over. All right, that's 53 is the encrypted message. And I would compute what is known as the multiplicative inverse of E, a D such that D times E equals 1. So then if I do M to the E to the D mod P, this would equal, again, middle school arithmetic here, E times D mod P, which would equal M to the 1 power mod P, which would equal M mod P. Decryption. E is the encrypting key, D is the decrypting key. And because I only know D, then all you can do is encrypt to me. If you share the public key, that's fine, it's public. Whereas if you shared an AES public key, or there's no public key, if you shared an AES key, then anyone could decrypt the data, or someone hacked you and leaked the AES key. They could decrypt the data that you are sending to me encrypted. Whereas with this, with just E, they can't. They need this D. Now, what is D in this context? We don't even have it. As you can tell, it's not defined. So we need to come up with it. D is a number where E times D mod P is 1. Now, with 71 numbers defined by P, right, we can just start guessing. So we can say, okay, well, hey, what is, we can very quickly brute force this. For D in range P, so every number from 0 to P minus 1, if D times E mod P is 1, break. All right. So now we've looked over a bunch of numbers, found a number D is 24. D times E mod P is 1. Cool. All right. Of course, another way to find it, if P is just a simple prime, right? So we do basically P plus 1. Will this work? Divided by E. Yeah, 24. Cool. Okay. So we brute forced the number, the multiplicative inverse in the modulo, under the modulo P of E. And so now we should be able to do this, right? If M is 11, M to the E mod P is 53, and E to the D, M to the E to the D mod P is not 11. Why? Why didn't we decrypt correctly? Exactly. I spent all this time talking about distortion, and actually I messed up. I realized that a couple commands ago that I was computing the multiplicative inverse under P and not under the totient of P. What I need is the multiplicative inverse under the totient of P. If we change this to encryption is M times E instead of to the E power mod P, and decryption is multiplying it back out by D, then this works. This gets us back to 11. But the exponentiation, it doesn't work. So now we need to redo our D search here. And what we actually want is a multiplicative inverse to find the multiplicative inverse of E under the totient of P, which is for prime numbers P minus 1. Awesome. Okay. Now we try this again. So M to the E, old news, it's 53. M to the E to the D, back to 11. Magic, right? Mathematical magic. Now, let's say you wanted to encrypt like The number 5, I mean, if you're trying to tell me, you know, what day your birthday's on or something, you can encrypt the number and send it along. But realistically, you want to send like data, right? How do you send data? Well, you send data by taking the ASCII values and just converting the data into one big number. So, for example, that's one way you can send data. So if we have, I don't know, come to my birthday party, this is our data. It's a byte string here. Every one of these bytes, we can actually convert this to a list of numbers, right, of the ASCII values of these letters. And then we just kind of combine them. And actually, there's a helper function here to, we need to assign this first to a thing. So m text is this, and m is m text. That is it to int dot from bytes. So we, well, okay, then we could just do that. Okay, come to my birthday party. Okay, and then we have to pass in what is the order, like when you lay this out into a number. Hypothetically speaking, are you going to do 99, 111, 109, 101, conceptually speaking, or starting to them back 121, 116, 114, and there's number of reasons for one over the other, et cetera, et cetera, et cetera. We'll get to maybe in a module and a half, but realistic. But you know, we just pick one, and it's called little endian. Lay it out in this direction. So this the y of party first, or big endian coming from the C of come to my birthday party first. All right. And this gives us a number. Now, this number is very large. It's larger than our 71 modulus, and so it's not going to be good. It's not going to be good is not very specific, but we won't be able to actually express it in a in numbers from 0 to 71 or from 0 to 70, no matter how heavily we encrypt this thing. But of course, if our P was much bigger, do you remember crypto.rsa? Import crypto. Let's grab a key generator from here. Okay, import crypto dot. All right, this is pi crypto dome RSA generate. That public key? Yeah. Yep. Okay. So that public key dot RSA. Do you see what's happening? Nix is happening. Okay. We're going to see how big our message is. Our message is about 100, almost 199 bits long. So we need, let's say, a 256-bit prime. I'm just going to Google for one. This is a terrible idea. Don't Google for your primes. But we're just going to grab a prime off the internet. Boom. Okay. Someone has very nicely given us, let's grab a 256-bit prime. Why does the number look like this? Oh, 10 least case for which, that's not what we want. That's not a prime. Oh my God. Here we go. Yes, give me primes. Number of bits. Don't do this for your primes. Perfect. Okay, now here we go. This is one of our primes. So we're going to take this prime, copy it. Generate primes in the safety and comfort of your own home. We're going to paste it in here. Okay, and we're going to paste it here. So now our new P is this monstrosity. Our M is the encoded number. As a reminder, it was this. Our E remains 3. So M to the E mod P, there's going to be probably very, oh, no, it was fast to calculate. This is our encrypted, our ciphertext. And then if we raise ciphertext, oh, we need to compute our D. Now, if we do our old for loop again, this will never terminate because we're looping through 256, 2 to the 256 possible combinations of the inverse of P. So that's not very nice. Now, again, given that P is prime, wait, what does keep us from doing this? Nothing, right? So if we do D equals, just don't want people to get into this habit. Oh, that doesn't work. Not for real numbers. For big numbers? I don't believe it.
You pass the models.
Yeah, watch what'll happen. Okay, so we compute the multiplicative inverse, which is e to the -1. So then we do e times e to the -1. That's e divided by e equals 1. Mod p. Oh, shit. But if p was composite, that wouldn't work.
Well, you need the totient, but yeah.
Well, yeah, I need a totient, but okay. Anyways, mind blown. Maybe this is a bit of a.
It's using Euler now.
It is for real. Python does this natively now. Back in my day, you needed crazy libraries to do this. All right. Anyways, doesn't matter. So now we have the multiplicative inverse of p. There'll be a quiz in a second. Okay. Oh, I didn't do d equals. Okay. D equals that. Boom. All right. So again, we have our crypto ciphertext and C to the D mod P. Okay. Don't do that. This does a very inefficient thing where it computes, takes C, raises it to the D, which is a massive number and it'll never finish. Oh, maybe it will, but just use the intelligent algorithms that Connor mentioned earlier. It's Python's POW function. Boom, computes it instantly. This should be our decrypted message. So here's our decrypted message. And what we want to do, we say MD, message decrypted. And then we, is it 2 bytes? 2 bytes. We say how many bytes, and I don't know if it was 200 bits. Let's just do 256 bytes, whatever. It'll be a bunch of 256 zeros padded. And then it was little endian, so start encoding it then. Boom. And we get, come to my birthday party. Or do we? We got a bunch of garbage, even after we strip away all of the zeros to that pad. Because we stretched it out to 256 bytes. What happened? Why did the decryption go haywire? So I'm going to bring up all of the commands I ran. Here's where I encrypted. Okay, M to the E. Then I realized, oh shit, I need to compute a D. I computed the inverse, multiplicative inverse of E under mod P. And then I raised C to that power. Yes. Yes. I again didn't use the totient. All right. So again, D is not the multiplicative inverse of E mod P. It's the inverse of E mod the totient of P, which for a prime number is P minus 1. It's a factor of, wait, is it? Does this make sense? So P is P prime. It's possible that our like, since we copied this prime off the internet, which you should never do under any situation, any scenario, we can ask ChatGPT if it's prime. No, that's a terrible idea, of course. Factor DB is actually a cool idea. Here's a cool website. You put in numbers and it will try to factor them. This is a prime number. What does PRP mean? Probably prime. Wait, did I say probably or provably? Probably. What if it's not prime? All right. Since we don't need, since POW can do the multiplicative inverses, we're logging out of this IPython. Oh, what's going on? Okay. And we are hitting normal IPython, where I have access to boom. And then we're just going to generate a key. .256-bit. Here's our key. No, come on. Fine. It doesn't matter. 1024-bit. We've left the land of easily understandable numbers. Okay. Here's our P that we're going to be using from now on. Now E remains 3. M is our encoded guy. And now we need to compute D. Boom. All right. So the previous thing was probably not prime. And then still that. All right. Whatever. We're not going to dwell on it. All right. We have an M to the E mod P. Again, let's not do it this way. We'll get in the practice of going E to the M mod P. Boom. That's our encrypted message. And to get, now that we've computed the correct D, we get the decrypted message back. C to the D mod P. And there's the decrypted message. And then we do md.2 bytes. Boom. That's unexpected. Is it a problem if E is too, it shouldn't be a problem if E is too small. E, oh, oops. What did I do wrong? Here's the history. All right. What did I do wrong? M to the E, not E to the M. Okay. Here. Yeah, here is where I went wrong. So we raise M to the E power mod P. And then to decrypt it, we raise that to the D power. And then when we decrypt it, come to my birthday party. Okay. Now we're in business. We can encrypt, we can decrypt. And when we operate under the modulo in an exponent, we do so with the totient function. Awesome. Now, the public information is P and E. I just hand that out to everybody. Connor has it. You all have it. You can all send me birthday party invites. And only I know D, because I could calculate it from the multiplicative inverse under the totient function. What's the problem here? security issue. What if you intercept a message, you know P and E, because I gave it out to everybody. So if you want to secretly invite me to your birthday party without inviting the rest of the class, no problem. Just encrypt your message with this and send it over. And Connor grabs that message, the encrypted message. Connor grabs C. What's the issue here? Yeah. So can Connor subtract 1?
I think so.
He thinks so. And clearly, Connor knows how to use the POW function to invert E because he just did that, just told me to do it, whereas I was reaching for the old elegant tools of the past. So he just grabs P, subtracts 1, takes E, raises it to negative 1 power, mod P minus 1, and you're done. And he has D. And he decrypts the message. And he shows up at the party, and both of us are there, and it's really awkward. So what do we do? The totient function is very simple to compute for a number when it's a prime number. But, and this is just how mathematics work, if it's not a prime number, if we are operating under a modulus that is the product of several numbers, and we use 2 in the RSA case, so we have key.p that we had, and we also have key.q. It's another very large number. And if we have p and we have q and we have n equals p times q, and we do everything under the modulo n, which is a product of 2 numbers. Again, we have our m that is come to my birthday party. We have our e, let's keep it at 3. Our modern RSA uses a hex 10001. It doesn't, for extremely complex cryptographic attack reasons, but 3 was perfectly fine for a while. Then they made it 7. Then now it's very big. All right, anyways, doesn't matter. And then we do, boom, m to the e mod n now, right? Awesome. And now we need a d, so we do compute the multiplicative inverse under the modulo n minus 1, and it doesn't work. And it might even work for certain ones, but it doesn't work here. What should we actually be computing for our d? Exactly. The totient of a composite number is, think of it like the exponent of a composite number. If I do 5 times 2 to the 3rd power, that simplifies or distributes into 5 to the 3rd power times 2 to the 3rd power. In the same way, the totient of 5 times 2 is going to be the totient of 5 times the totient of 2. So the totient of what is fundamentally p times q, it's not p times q number minus 1. It is p times minus 1 times q minus 1. So keep in mind, when we did the encryption, we didn't need p and q. We just needed n. But to do the decryption, to calculate d, we need p and q. And then once we have that, we do a POW of a c to the d mod n. And then, oops, I overwrote my message. 1 sec. Let's get the message back. Our decrypted message is c to the d mod n. And then we can get the bytes back, and boom, you're all coming to my birthday party again. Okay. In order to do that, the only place in this whole thing here where we needed P and Q was to calculate the decryption key. Everything else, all you need is N. So I calculate P and Q, and I tell you all the key N and the number E. Most of the time, the number E is nice, fixed, commonly globally known number. So I tell you N, but I include E just out of, convenience for you. N is a huge number. It's the product of two primes or some amount of primes. There's also such a thing as multi-prime RSA for various reasons, where N could be the product of, 5 primes. There's various security issues with that, et cetera, et cetera. But normally speaking, P and Q are two massive primes. I keep them secret. I don't actually even need P and Q. I just need D, right? Like I just use P and Q to compute D. But either P and Q or just D alone are my private key. N is the public key, and E. And then you can send me messages. And unless you know P and Q, you can't, or someone else can't decrypt those messages. Now, what keeps you from just taking N and factoring it, right? If N was 25, what are the prime factors of N? 5 and 5. What if it was 15? 3 and 5. What if it was 1111473769355692820, et cetera, et cetera, et cetera, right? Obviously, you're not going to be able to do it, but hey, guess what? A computer won't be able to do it either. I mean, a quantum computer can. But just like we discussed that last time, that there is a world record in the discrete logarithm problem. Did we discuss this? And it's like discrete logarithm under the modulo is 761 bits. There's also a factoring world record. It's around the same, maybe a little bigger, maybe a little smaller. I honestly don't remember. You can look it up on Wikipedia. Like you can get into Wikipedia for beating this, but realistically, where RSA keys are at nowadays is more in the 2000s of bits or whatever. And without a breakthrough in mathematics or a breakthrough in physics to build functional quantum computers that work at this scale, you're not going to be factoring these numbers out. Now, once we get quantum computers that work at this scale, RSA is cooked. Diffie-Hellman, gone. Right? So these are, when you hear the words post-quantum crypto, these are not post-quantum. These are very, very much pre-quantum crypto. But it's effective, and it runs basically the internet today, RSA and things like it, much of the internet. All right. Anything else we want to say about RSA?
It's possible you could factor, we just don't know.
Yeah, that's right. Just to be very clear, there is no proof that we can't factor this without quantum computing. We just don't have an algorithm for it. So, if you're bored late at night, try to come up with an algorithm to factor this thing. If your algorithm has a loop where you increment by 1 and try to divide and see if it cleanly divides, that's not quite it. Okay. Now, some really cool stuff does happen. This is a bit of a tangent, but we'll just do it real quick. If you, for example, generate an RSA key and then your computer glitches, or you're running in a low, like a really constrained computing environment, and like, I don't know, it's like in space at a satellite, and a cosmic ray hits your memory and flips a bit. Well, guess what? It's very likely that if you have a prime number and then you flip a bit, your number might no longer be prime, and then you might end up in a situation where you're using, maybe this is more of a problem in Diffie-Hellman than an RSA, but suddenly you're using unsafe values. It's all right. Tangent aborted. Let's move on to AES. Any questions about RSA before we move on?
I think one other thing worth pointing out is that finding large primes is doable. You can do that fast.
Yeah, that's right. So
intuitive. How do you come up with a big prime?
yeah, there are very cool algorithms that will come up with very large prime numbers, and it's not any prime numbers. It turns out that there are certain primes, certain prime combinations that are unsafe with RSA, that have certain mathematical properties that extremely smart cryptographers have figured out how to do shenanigans with. But realistically, if you use, again, to reiterate an earlier point, an earlier point from last lecture, don't roll your own crypto. Use a library like Python's Cryptodome library. It's gonna generate fairly reasonable keys for you. And if it doesn't, well, you can blame them. At least you didn't mess up. All right, awesome. What next? So that's RSA. That is asymmetric cryptography. Again, cryptography where you can send me messages, you can encrypt them, but for you, it's a one-way function because of that totient that you cannot compute. All right, you can all encrypt it. You can send me messages. I can decrypt them all. The inverse is also true, by the way. I can take my message and I can raise it to the D and I can send it to you. And you can use E, which is the multiplicative inverse of D, which you already have, to decrypt it. So I can also broadcast out messages that everyone can decrypt, which sounds kind of silly. Why would I do that? But then, if I'm giving you messages that only I can sign, and it's like, hey, you got to cancel your birthday party because I made the assignment due right on that day, it's from me because I encrypted it with the value of D or P and Q that only I know. All right. And this is also like how, GPG signatures, for example, work on the internet. So you have your public and private key. I have my public and private key. You don't need to do these key exchanges. We just, boom, I encrypt the key, my message with the key. I send it to you. You do the same. Why wouldn't we base all of our encryption cryptographic technologies on this model? I don't know. It's because it's slow. Because you saw we have fast algorithms to do certain things, but oops. But when you saw I accidentally did, once the numbers got large, accidentally did this, and then it just kind of sat there for a while, working very hard. Like the optimized algorithms are much faster, but they're still on the slower side. One of the reasons that E is so small, like it used to be very small, it used to be 3 or 7 or whatever, and then it nowadays is still small compared to the rest of these numbers. Hex 1001 is 65537. That's still pretty small. This is for performance, especially, not on your desktop, but on like a super constrained processor running a satellite, all this fun stuff, right? With symmetric crypto, things are typically much, much faster. So AES, for example, is a lot faster than doing all of this stuff. And so typically what happens when you want to exchange a whole bunch of encrypted messages, you use something like Diffie-Hellman or even RSA, basically to exchange the key, and then you switch to AES or something like it. So now let's talk about AES or something like it. AES, RSA is very approachable, and Diffie-Hellman is very approachable with kind of middle school math, right? Like, it's multiplication, exponentiation. Modulo is the one complex thing. Did we talk about what the module is last week, right? Or on Monday? Yeah, we did, right? Talked about division and remaindering. Who here is unclear on what the modulus is? Modulo, okay. Sweet. Did anyone, who here is clear on it? Better question. All right, also nobody. So we're all in kind of a quantum state. A couple of people clear on it. If we have 10 and we divide it by 3, the result is 3. Everyone with me so far? Awesome. Now, 3 doesn't, we don't want to work with fractions for many, many reasons. So if we were in middle school, or I guess elementary school now, or you're going backwards in life, and you did 10 over 3, and then you say, well, that is 3 1/3, right? So 3 is the whole number division result, and 1 is the remainder. Modulus is the remainder of the division. And so when you are operating under the modulus 71, every number gets divided by 71, and the remainder is returned. Okay, cool. Now, I have to reconceptualize all the earlier discussion in that. But for the next 25 minutes, we're in AES land. All right. AES, unlike RSA, which is all about division, multiplication, et cetera, et cetera, et cetera, AES is a whole bunch of matrix math. Who here remembers addition and multiplication? Nice. Almost half the class. All right. How about matrix math? All right. We got a couple of people, about half as many. So not going to dive in and make you remember and live all of your matrix math. We're not going to go into implementation flaws within AES. We're just going to say, you know what? AES works. And realistically, all the information that we have right now is AES works. It's possible that someone somewhere in a secret room has a magic wand that they just like tap against the computer and break AES, but we're just going to assume this isn't the case. So for us, AES is going to be just something that takes a message and a key, and it returns something, does something and returns. How did that compile? It must be IPython stuff. Okay. It does something weird and returns the ciphertext. And the weird stuff that it does has to do with, you know, a bunch of matrix stuff, and then you shift some rows, and then you mix some columns, and then you do some crazy stuff, and that's fine. AES takes 128 bits of input, 16 bytes, and a key that, depending on what flavor of AES, is either 16 or 32 bytes long. And then it returns an encrypted block of data that is 16 bytes long. And now I'm going to go and just launch an AES level so I can just crib off of the source code there. Okay. Boom, boom. AES. Okay, here's AES. Create a key. We create an AES instance in PyCryptoDome, and then we encrypt stuff. Now, the caveat with AES is it takes 16 bytes. No more, no less. RSA took a number that we encoded our text into. AES takes 16 bytes. And if you give it less than 16 bytes, it tells you that you're a bad person. Like this. I'm just pasting all of this stuff. I should, okay. And here we go. So let's say we want to encrypt birthday. Boom. Data must be aligned to block boundary. Now, there are modes of AES where this isn't the case. But, or rather, applications of AES, layers built on top of AES that will support encrypting a single byte at a time. Because for some things, you actually need to do that. If you're streaming video and you don't have a nice, clean 16 bytes boundary to send. Realistically, probably not video, but if you are, I don't know, streaming some sensor data in some constrained environment, you don't want to waste bandwidth. But for just normal, everyday AES, it's got to be 16 bytes. So, of course, you can just use Pythons like ljust, which will justify the string down to some, or up to some size. So this will left justify birthday exclamation point with probably a bunch of spaces, right?
See the result?
Well, yeah, let's see. There's okay, so we encrypted it and then we do cipher.decrypt, ciphertext. And the result, yep, with a bunch of spaces. Results birthday with a bunch of spaces. Now, you can do that. That's fine. Again, we're trusting AES to do its thing here. One interesting thing, we're not learning about the internals of AES. We're learning about how the existence of AES is then applied to build crypto systems. The interesting thing with this is in all of these levels here, this entire challenge series from AES all the way down to AES, CBC, POA, encrypt, you can substitute AES with any other symmetric cipher. You want to go back 20 years? You can use DES. No one uses DES, but you could. And these challenges would remain the same, just a different block size. You could use, you know, any other of the like super hipster block ciphers that just, you know, realistically you should just use AES in your everyday life. But these attacks apply to any block cipher, which is super cool. Okay. So cipher attack, some random stuff. When we decrypt, it's birthday, but if we pad with spaces, how do you tell the difference between encrypting birthday exclamation point and encrypting birthday exclamation point space, 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 space? They encrypt to the same thing once they're padded. And you shouldn't have that. You should strive to avoid a situation where two different messages encrypt to the same string. This is one such message, and this is another such message. Same string. No good, right? So what you want is a better pad function that pads things in a way that's kind of very clear to unpad and unique to unpad. And we have it, and it's provided by Crypto.Dome, and it's called PKCS7. PKCS7 is a public key crypto system, PKCS standard, public key crypto standard. Anyways, PKCS7 is a standard with a bunch of different things, including a padding style. And so we imported this pad function from Crypto.Dome, and we can just pad birthday, and you can see what it does. And of course, it needs to know how much to pad it to. And basically, it figures out how many bytes it needs to pad to get up to the block size. That's 16 for AES. And then it pads with that many bytes, each of which has that value. So that when you decrypt, it just looks at the last byte and says, is this a number between 0 and 16? If it's the last block that is decrypted when you're, when you're unpadding it. Let's encrypt or import unpadding as well. Here's the pad. Here is the unpad. Also block size. And it just removes it. Nice and easy. Okay. One caveat. if you already have something that is 16 bytes long, let's say I am encrypting a terabyte scream, right? If we try to unpad, or if we encrypt this, we don't need to pad it to get it out to the block size. If we try to unpad it, when we decrypt it, we want to know, should we unpad this thing? We look at the last byte, if it's the last block, right? And we say, okay, well, that's bigger than 16, so we're not going to unpad it. But what if I was encrypting instead a bunch of new lines? A new line, we can use the ORD function to get the ASCII value of the new line. That's 10, or hex A. That is a valid padding amount. If we actually did this and we had this as our text and we tried to unpad it from block size 16, it would actually unpad successfully. And now, if we're encrypting a bunch of new lines, like, for example, you have a document you're AES encrypting and there's just a blank page, suddenly you have things going a little haywire. So what happens when we pad something like this with BKCS7 or any real padding standard? We try to pad it, it'll actually give us a whole extra block with nothing but padding. Hex 16 or hex 10 is decimal 16, so there's 16 bytes here, all with padding. And this gets important in the later AES levels because of how you careful you have to be with padding there. Okay, so padding in AES, fairly important. But right now, we're kind of, AES, again, is a magic box that encrypts 16 bytes. So now we have 32 bytes. So what's going on here, right? Well, what do we do with 13 bytes? If we try to stuff this into AES, and actually AES is not used in this way to the extent that I can't actually demo this error because there is no way to run AES in a real crypto library like ByCrypto. To my knowledge, in single block mode. I'm sure someone will say, oh, this is how you do it. That's awesome. But by default, the interface that I'm using won't even automatically deal with this stuff. But, you know, if I want to encrypt 32 bytes, I encrypt them separately, right? And realistically, the encrypt function deals with this automatically. So if I encrypt my padded version, I pad all my new lines to 16. So that results in 32 bytes, the last 16 of which are padding. This gives me 32 bytes of output. Now, AES encrypts 16, returns 16 bytes. How the hell did I get 32 bytes? Well, it has to do with how I defined my cipher here. Said, hey, let's create a new AES cipher object that has that key and has a mode of ECB. Now, this mode is the block chaining mode. Basically, how a block cipher deals with multiple blocks. Because in order to do anything, most useful things, you're going to have to encrypt more than 16 bytes. Right? 16 bytes. Even a birthday party invite is going to be more than 16 bytes long. Come to my birthday party was more than 16 bytes long. And so in order to encrypt that, I have to figure out, how am I going to split up the data? That part's easy, just 16 bytes at a time. How am I going to encrypt every block? How am I going to combine the output, etc. Right? And there's a bunch of modes that are created by a bunch of cryptographers. And the meme one that is never used in practice, should never be used in practice, but is really nice for the classroom, is ECB mode, the electronic code book. ECB is this brilliant thing that says, hey, you got 2 blocks, We just encrypt them separately, right? So this guy, encrypted in ECB mode, is this. There are 2 blocks here. That's the first. That's the second. And in fact, if we didn't, instead of padding this thing, we had 2 blocks that were the same. So times 32 here. And we took a look at the first block output. And we looked at the second block output. Where is it? Must have passed it there. They're the same. Just chops up the block and encrypt separately. Now, there are problems with this. We don't have time to actually carry this out. Maybe we will tomorrow. I'll show you a preview of it. So if you look at the Wikipedia article for block cipher modes of operation, and you look at ECB, because we have to talk about ECB, it's a good meme. If you encrypt using ECB, something like this image of the Linux penguin mascot, using ECB, all of these black parts and all these white parts, 16 bytes at a time, encrypt to the same thing. And you can just take a look. You can see, oh, this message, this image was the penguin, right? You get a pretty good idea, 16 bytes at a time, except for in places where there's like high difference. But even there are patterns that you can kind of see over here, right? That's what ECB gets you. And where's my pwn.college? And it's from exactly this, from the fact that we have the same multiple duplications or whatever, multiple instances of the same block value in plain text, resulting in the same value in ciphertext mode. This, let's see, we have like 7 minutes left. On Twitch, we have a comment. So ECB is like the 90s cable scrambler for Cinemax. That's exactly it. So it used to be that, and I honestly don't know how things work now, but if you had, there were premium channels, let's say sports channels or something in cable, and your parents didn't pay for them, and you're scrolling through the channels, well, you would still get some image, but it would be scrambled. The color, it would look like that penguin. And I don't know if it was specifically CB. Well, definitely not, because this predated AES. But it could have been some conceptually similar thing. But yeah, basically the effect is like that, and then it's a problem in real world crypto. The nice thing about ECB is it's so simple, so you can reason about it very simply, but also so you can the encryptor and the decryptor are both basically random access. You can encrypt anything. If I have a 10 terabyte file and I want to encrypt just one, I don't know, if I have a 24-hour video, I want to encrypt just 1 minute of it and send it along. Easy to do. Pull it out random, encrypt the blocks, send it. It's a bad idea. Better to have other thing, but ECB can work for that. Same with decryption. If I receive a 10 terabyte file encrypted, I can seek into the middle of it and just decrypt 1 block. There are other modes that are much safer that allow that to happen. Still, point is, block ciphers themselves, for the purposes of this module, are just magic boxes. How you combine the output of those magic boxes, that's really where we are going to be focusing on the challenges here. Questions about AES? Connor, do you have any questions? All right. So it's AES, that's RSA. Other parts of this homework are figuring out how to mess with data. One thing that we haven't talked about in the context of RSA, because it doesn't apply there, but it does apply in the context of AES in other cipher modes of operation is XOR. An XOR is basically a controlled bit flip. So if we have something like hex 111011, actually, let's do the number, the letter A. So we have this hexadecimal number, which is A, not X, sorry. This, not hexadecimal, this binary number. That's A. And we XOR it with, let's say 0110, let's say 1110. We XOR it with some bit mask. We get our / 2F. And if we look at the binary value of this cuts it off at the largest one. But basically, every every pair of bits that were the same, it puts into a 0. It makes a 0, and every pair of bits that are different, it makes a 1. Right. So this bit got flipped to 0. Oops. This bit got flipped to a 1 because they're different here. And basically, this controlled way of bit flips is undoable. So in the same way, if we get the ORD of a / and we XOR it with OB 0110 1110, and we transform that back into a character, we're back to our A, right? So in some sense, this is encryption with a key of some crazy bit string. We make that key big enough and random enough and secret enough, and this is our only proven safe crypto system. AES has no proof of security. RSA has no proof of security. In fact, we know that RSA will fail once quantum computers get up and running. But tomorrow, in your spare time tonight, one of you could invent a factoring algorithm and change the world and break RSA, or get really curious about how AES works and do a Wikipedia dive and realize some fundamental flaw deep inside and destroy modern secure communications. But we have a proof that if I have a long, completely random bit string and I share it with you secretly, that data is unbreakable. But then I have to keep refreshing my secret bits with you, and it's just not functional in practice. You might say, hey, well, what if you use Diffie-Hellman to come up with these bits, secret bits? Well, now you build a crypto system on top of Diffie-Hellman, so which we don't have a proof of security for. So you have reduced the security of the one-time pad to Diffie-Hellman. That's XOR. Now, say, why am I talking to you about this mean crypto system of a one-time pad where no one's going to be exchanging these pads? In more advanced AES cipher block modes of operations, we use XOR. For example, to solve the penguin problem, I could use a penguin problem solution for some other situations right now. We keep having to stream on Connor's laptop because my Linux laptop isn't. All right. Anyways, you can solve this penguin problem with the way that the next textbook way to solve it is what is called cipher block chaining, where we take the plain text, and before encrypting that plain text into the ciphertext, that block, we XOR it with the ciphertext of the previous block, which is some random shit. And so then we basically eliminate the penguin pattern, and things are secure. And you will then also learn through the challenges how to break certain situations in cipher blockchaining, which is what that's called. One more thing I want to say about that. Oh, the downside, in order to send you, say, the penguin's tummy, I can't, with ECB, I could just encrypt the tummy and send it over, right? With cipher blockchaining, this next one, CBC, I have to encrypt from the very beginning because I have to XOR the previous block to generate, to encrypt the block, the previous ciphertext to encrypt the plain text. And to get the previous ciphertext, I have to XOR the ciphertext before that, and so on. So you lose this random access encryption, but you still have random access decryption. You just have to send me the previous block as well. Anyways, we go into all of this in the challenges, and we'll talk about this next week. But I think you should now be fairly equipped tackling some concepts of hacks and ASCII and base 64 to dial in all the way through the checkpoint. All right, let's do it. All right, we have the millennial pause at the end as I search for the stop stream. You got to have a hotkey.